In this video, we're going to prove the average theorem, which is really a way of saying that ordered fields are not discrete. So recall that if f is an ordered field, then we can find a copy of the natural numbers in that ordered field by just summing up the multiplicative identity a bunch of times. So if we form this set n, which will contain 1, 1 plus 1, 1 plus 1 plus 1, and so on, in any ordered field, then that set will have all the properties of the natural numbers. Okay, so we can identify those elements with the natural numbers. So we'll just refer to them instead of as a copy or as identified with the natural numbers. We'll just refer to that set within the ordered field as the natural numbers. Okay, 1, 2, 3, and so on. Now, we have ordered field axioms that guarantee an additive identity and additive inverses for elements of the field. So that means that within f, if we have a copy of the natural numbers, then we also have the natural numbers plus 0. We also have the natural numbers plus all of the additive inverses, -1, -2, and so on. So we have a copy of the integers. We have a copy of z. So for this discussion, there are going to be two important differences, though, that you should notice between the axioms for an ordered field and the axioms for the natural numbers or the integers. First, in an ordered field, any non-zero element has a multiplicative inverse. Okay, that's not true in the natural numbers or in the integers. Also, there are no ordered field axioms asserting that an ordered field has to be discrete. So for both the natural numbers and the integers, we came to the conclusion they were discrete sets, that there was a gap between subsequent natural numbers and subsequent integers. There's no ordered field axiom asserting that it has to be true of an ordered field. And in fact, the average theorem will say exactly the opposite, that ordered fields are not discrete. So the average theorem is stated as follows. Let's suppose f is an ordered field. A and b are elements of f with a strictly less than b. Then there is an element r in the ordered field between a and b. So a is less than r is less than b. And in fact, we can just take r to be the average of a and b, that is a plus b over 2. That's an example of an element of the field that's strictly between a and b. So this is a pretty easy theorem to prove. The statement of the theorem actually tells you how to prove it. Let's assume that f is an ordered field. Let's assume that a and b are elements of f and that a is less than b. Then we can add a to both sides of that inequality, and we'll get a plus a is less than a plus b. In other words, we'll get 2a is less than a plus b. We can do the same thing with b. So if we add b to both sides of that inequality, a less than b, then we'd get a plus b on the right-hand side is less than b plus b. That is, a plus b is less than 2b. Okay? So that means by transitivity that 2a is less than a plus b, which is less than 2b. And then, of course, we can multiply that inequality by the multiplicative inverse of 2 to obtain that a is less than a plus b over 2, which is less than b. And that concludes the proof of the average theorem. So what's the import? Why is the average theorem important? Well, let's recall that the integers and the natural numbers are discrete. That is, they both satisfy the condition that if n is less than m, which is less than or equal to n plus 1, then n has to be m plus 1. In other words, there's no natural number between another natural number and its successor. There's no integer between an integer and its successor. Okay. So on the one hand, we have that there are no integers between two consecutive integers. And so we can picture that if we pictured the integers laid out in a line, you might picture them as sort of independent little dots with a gap between them. Okay. In contrast, the average theorem, though, says that between any two numbers in an ordered field, there's another number. So there are no gaps like that, right? And you'd have to picture an ordered field with no empty gaps, because if you had a potential gap, you could just stick another field element within that gap. Okay, so we might picture an ordered field like we did as sort of a solid line. But consider something like the rational numbers. We happen to know that this is an ordered field. So the average theorem applies, and it tells us that between any two rational numbers we can find another rational number. Okay. So there are no gaps in the rationals. And so, on the other hand, though, we know that there are numbers like root 2, which are perfectly good numbers, but which are not rational numbers. Okay. So we might say there are holes in the rationals, but no gaps. So there are missing numbers here and there, but no sort of long continuous stretch of missing numbers. Now let's take an ordered field like Q adjoin root 2. Now that has some of the holes filled as compared to Q. So for example, root 2 is an element, and a bunch of other sort of rational combinations of rationals in root 2. In other words, it contains some numbers that are not contained in the rationals. But even Q root 2 has holes. So for example, you could prove that root 3 is not a member of Q root 2. Okay, so if you pictured the rationals as sort of a gray line, you might picture Q root 2 as a slightly darker line. It's got a lot of things filled in, a lot fewer holes in a sense, but it's still got some holes. Ultimately, our goal is an ordered field with no gaps or holes. Okay, so we want a complete number line that we could sort of imagine as a solid dark line with no holes and no gaps. And what we're going to show is that that will be the set of real numbers, R. So that concludes this proof of the average theorem and a little explanation of what it says. Thanks for listening.